Hello and welcome back to Unit 6 on circular motion and universal gravitation. In this part, we're going to look at examples using the law of universal gravitation. In the first example, we're going to consider the question, how fast does an apple need to go in order to orbit the Earth at the location of the moon, or basically at the same distance from the Earth as the moon? So here is the Earth. Here is the orbit of the moon, and there sits the moon, and right next to it sits a pretty red apple with a red leaf there you go. For this one, the net force equals mass times acceleration, but since these two objects are moving in a circle, the net force takes on the centripetal form. So that becomes mv squared over r. The force causing either the moon or the apple to orbit is the gravitational force. So I'm going to plug that in. The gravitational force will be the mass, the gravitational constant, times the mass of the Earth, times the mass of the object that is orbiting. So this is either the moon or the apple, little m, divided by the distance squared. We see that the mass of the object that is orbiting, little m, cancels. And now I can find a formula for the velocity. V will equal the square root of g times the remaining mass divided by the distance, where this remaining mass is going to be the object that is orbited. In our example, that would be the mass of the Earth. This formula does not depend on the mass of the thing or the object that is orbiting. That means that for an apple to orbit the Earth at the same location as the moon, it must move at the exact same speed in the orbit as the moon does. Now let's take a trip to Mars. Mars is orbited by two moons, Deimos and Phobos. I give you the mass and the distance that each moon orbits Mars at, and I also give you the mass of Mars. Okay. The first question I have is, given the orientation shown, what is the net force on Mars? And then we want to find the orbital speed of Phobos and the orbital period of Phobos. Okay. First off, notice that Phobos orbits at 9,377 kilometers, while as Deimos is orbiting at 23,460 kilometers. That makes this moon, Phobos, because it orbits Mars more closely than Deimos does. Okay. We can find the gravitational force from each moon on Mars. So the gravitational force from Phobos on Mars, I'm going to put a little p there, equals, oops, that was not meant to be a F, that was a G, capital G, the mass of Mars times the mass of Phobos divided by the distance between Mars and Phobos squared. Using the numbers on the previous page, I can now calculate how big this force is. The mass of Mars was 6.42 times 10 to the 23rd. The mass of Phobos is 1.08 times 10 to the 16th kilograms. And the distance between Mars and Phobos was 9,377 times 10 to the 3rd meters squared. And if you put that all correctly into your calculator, that works out to be 5.26 times 10 to the 15th newtons. I'm now going to find the magnitude of the force between Mars and Deimos, doing the exact same calculation, but plugging in the values for Deimos's mass and its distance. Oops. I skipped a line. There we go. And that works out to be the 1.56 times 10 to the 14th newtons. I'm now going to consider the free body diagram of Mars. We had Phobos up here, which means the gravitational on Mars will be here, and Deimos was off over here. If I set up a standard XY coordinate system, then I can write that the gravitational force between Phobos and Mars will be 5.26 times 10 to the 15th newtons in the positive y or j hat direction. For Deimos, I have to do components. This angle was given as 45 degrees, if you look. That means that the force will be cosine of 45 in the I hat plus sine of 45 in the j hat. I can now take and find the net force by adding the two pieces together. Okay. In the I hat direction, I only have the x component of the force due to Deimos, which is 1.10 times 10 to the 14th newtons. In the j hat direction, I have both the force from Phobos and the y component of the force due to Deimos. And if you add those two together, you get 5.37 times 10 to the 15th newtons j hat. The next question was to find the orbital speed of Phobos. To find the orbital speed, we can use the formula that we derived in the previous example, looking at the apple and the moon, where, remember, this mass is the thing that is being orbited. So that would be the mass of Mars. So the orbital speed will be 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of Mars, which is 6.42 times 10 to the 23rd kilograms, divided by the distance between Mars and Phobos, which was 9,377 times 10 to the 3rd meters. And if you put this all into your calculator correctly, you get a value for the orbital speed of Phobos as 2,136.97 meters per second. The last part of this question asks for the orbital period. To calculate the orbital period, there is an assumption that is going to be made, and that is that the moon is going to move in a circle at constant speed. That allows us to write the speed as the circumference of the circular orbit divided by the period. Or in other words, the period will equal the circumference divided by the velocity. And putting all of this into a calculator results in 27,570.5 seconds. I don't know how you feel, but I look at that and say 27, not even 28,000 seconds. Okay. If you think about 1 hour being 3,600 seconds, that equates to a period of 7.66 hours. So Phobos orbits Mars once every 7.66 hours. And if you Google information about Phobos, you will find that that is a correct value. For the last example of this part and this unit, we're going to not orbit for a minute. We're just going to think about two objects that are attracting each other, something that we've been doing all semester. So here's my Earth, and it could be Jupiter or the Moon, but for the moment, let's just let this be Earth. And up above the Earth, I'm going to have a ball. And I want to know, what is the acceleration due to gravity between the Earth and the ball? Now, you should know the answer to this. We know that that ball will fall with an acceleration of 9.8 meters per second squared. But what is really cool is that we can calculate it. Okay, well, not that either. We need to make a couple of assumptions. Here is the radius of the planet. It could be a moon, but I'm just going to use RP for the moment. And we're going to assume that the ball is a height h above the surface. Now remember, every time we've done this, we've said, let the ball be near the surface of the Earth. Okay? In order to keep the ball near the surface of the Earth, to keep with that assumption, we're going to let the distance between the center of the planet and the ball equal RP plus that height. And we're going to say that's approximately just the radius of the planet. So we're going to keep the height small compared to the radius of the planet, so it doesn't really contribute to the calculation. And now if I draw the free body diagram of the ball, it's got one force on it. That force is the gravitational force. So F net equals MA. So the net force is caused by the gravitational force. That'll equal the mass times the acceleration because they're in the same direction. Ball's going to accelerate toward the center of the Earth. I can now plug in the universal formula for universal gravitation. Okay. The mass of the object that is falling cancels. The mass, I guess by falling I mean the little object, the ball. It cancels. Okay. It doesn't come into this calculation at all at this point, which is convenient because thus far this semester we have always ignored the fact of whether it was a ball or a large car or anything. We just let the acceleration due to gravity be the acceleration due to gravity. So the acceleration due to gravity is the gravitational constant divided by the mass divided by the radius of the planet squared, assuming that we can make the approximation that we're not very high above the surface of the moon or the planet. Now we need some numbers. The mass of the Earth, we've seen that one a couple times already, 10 to the 24th kilograms. Oops, that is a P, that should be an E. The radius of the Earth is 6.371 times 10 to the 6th meters. The mass of Jupiter is 1.9 times 10 to the 27th kilograms. And the radius of Jupiter is 69.911 times 10 to the 6th meters. And the mass of the moon is 73.35 times 10 to the 22nd kilograms. And the radius of the moon is 1.7374 times 10 to the 6th meters. And I got all of these numbers by just looking them up on the internet. Nothing too exciting. If I take the mass of the Earth and the radius of the Earth and plug it into this equation, then I get that the acceleration of this object on the Earth calculates out to be 9.81 meters per second squared. Our 9.8 meters per second squared that we've been using all semester, all course. If I use the numbers for Jupiter, I get 25.93 meters per second squared. And if I use the numbers for the moon, I get 1.62 meters per second squared, which notice is about a sixth the acceleration due to gravity on the Earth. You may hear that number along the way. Okay. This concludes this part and this unit.